Good day, Doctor. This is the individual presentation on the fundamentals of the first law and the second law of thermodynamics. My name is Shoyuki, matrix number 225639. And this is the overview of the whole presentation. I will begin with the first law of thermodynamics. This fundamental law states that the energy is conserved. It can change form, but it cannot be created or destroyed. In closed system, energy change comes from internal works and heat transfer. For example, in an insulated room, a heater doing 15 kilojoule of work result in an 15 kilojoule energy increase. Then, if the room loses 10 kilojoule of energy as heat, the net energy change will be 5 kilojoule. For energy balance, the equation is simple: energy input minus energy output equals to energy change. In closed system, changes in internal energy dominated, while in open system, we must include mass flow and flow works, and it is expressed as enthalpy, which is H equal to U plus PV. In steady flow system, energy remains constant over time, meaning that the total energy entering the system equals to the total energy leaving it. This balance includes contribution from heat, transfer, work done, and also the energy carried by mass flow. So this will ensure the system operates continuously without energy accumulation or loss. The first law of thermodynamics is important in engineering analysis. It enables us to evaluate energy systems like gas turbine and thermodynamic cycles such as Carnot and Rankine cycle. Additionally, it provides framework to assess energy transfer between both open and closed systems, making it indispensable for system design and optimization. However, the first law of thermodynamics has its limitation. It doesn't explain the natural direction of processes, such as the heat flowing from hot to cold, and it neglects the real-world factors like friction, turbulence, and energy loss due to irreversibility. Furthermore, it assumes idealized condition, which limits the direct application in complex scenario. This highlights that the needs for supplementary principle like the second law of thermodynamics to fully address the practical challenges. As mentioned, the first law doesn't explain how energy flow. The second law provides the missing directionality by stating that the heat always naturally flow from hot to cold. The second law also introduced the concept of entropy, a measure of disorder or randomness in a system. It states that the natural process always progresses towards increased entropy in an isolated system. This can be also explained mathematically. Now, consider a heat flowing from a warmer room to a cooler surrounding. The system entropy decreases due to heat loss, but the surrounding entropy increases more significantly. So when we calculated the total entropy changes for the universe, the changes of the entropy of the system plus the changes of the entropy of the surrounding will be always positive value. So this will align with the second law, confirming that the irreversibility of the natural heat flow. So these are two statements of the second law that has to be introduced to enhance the understanding on the second law. Kelvin Planck's statement states that no heat engine can convert all heat input into works. Some energy is always wasted as heat rejected to a lower temperature reservoir. This is due to entropy, which prevents 100% efficiency. Clause's statement states that the heat cannot flow from a colder region to a hotter one without external works. For example, the refrigeration system used work to transfer heat from a cold interior to a warmer region. This is aligned to the second law regarding to the directionality of the energy. Another critical aspect of the second law is entropy generation. Entropy generation is a measure of magnitude of the irreversibility present during the process. Irreversible process such as friction, unrestrained expansion, or heat transfer through a finite temperature difference all contribute to entropy generation. This irreversibility will directly contribute to the degradation of the performance of engineering system. Hence, the second law sets the limits to the efficiency. Finally, let's move on to the importance of the second law. First, it sets the clear boundary between possible and impossible processes. For instance, heat will never naturally flow from the cold to hot unless work is supplied. It also defines the theoretical limits of the efficiency for the engineering system. So this will encourage the design of the system to be more efficient by approaching to the ideal system and to minimize the irreversibility occur. Firstly, I would like to introduce the refrigeration cycle. This cycle is widely applied in the refrigerator, air conditioner, and the heat pump. A refrigeration cycle operates through four main components, which are the compressor, condenser, expansion valve, and the evaporator. And these components are connected by a working fluid called the refrigerant. And the cycle is begin with the compressor, where both the temperature and the pressure of the refrigerant is increased, preparing it for the heat release in the next stage. Next, the refrigerant moves to the condenser. The refrigerant releases the heat to the surrounding and condenses into a liquid. Next, after leaving the condenser, the refrigerant enters the expansion valve. This component reduces the pressure of the refrigerant, allowing it to expand and prepare for heat absorption in the evaporator. Next, the refrigerant then moves to the evaporator, where it absorbs heat from the cold region. As the refrigerant absorbs heat, it will evaporate and providing cooling effects. Finally, the refrigerants will return to the compressor and a new cycle begins. In this section, we will focus on the ideal vapor compression refrigeration cycle, which is the most commonly used refrigeration cycle in various cooling systems. This cycle consists of four main processes, which are stage 1 to 2, isentropic compression, stage 2 to 3, constant pressure heat rejection, stage 3 to 4, throttling, Stage 4 to 1, constant pressure heat absorption. Now, several assumptions need to be made to simplify the analysis, such as steady flow, adiabatic compressor, and changes in the kinetic and potential energy are negligible in order to apply the steady flow energy equation to analyze the cycle. For the first process, which is isentropic compression, the refrigerant enters the compressor and the work is done by compressor on the refrigerant, causing the pressure and the temperature to rise. Since the compression process is adiabatic, all of the work done is converted into an increase in refrigerant internal energy and hence increase in enthalpy. The energy balance equation can be referred to in the slide. The second process is constant pressure heat rejection process. In this process, the refrigerant exits the compressor and enters the condenser. In the condenser, the refrigerant releases the heat to the surrounding. Since the process is isobaric and no work is done, then the heat rejected is equal to the decrease in enthalpy, and the energy balance is expressed as here. Now moving on to stage 3 to 4, the refrigerant now is a saturated liquid stage. It will pass through the expansion valve, and the expansion process is isenthalpic, meaning that the enthalpy remains constant. And during this throttling process, the pressure and the temperature of the refrigerant will decrease, but no heat and work is exchanged. Therefore, the equation will be H3 equals to H4. Finally, stage 4 to 1 is constant pressure heat absorption process, and refrigerant enter the evaporator. In the evaporator, the refrigerant will absorb heat from the space or substance being cold. According to the first law of thermodynamics, the heat absorbed is equal to the increase in enthalpy of the refrigerant from stage 4 to stage 1, and the energy balance is provided here. After going through the process one by one, the overall energy balance equation for the whole cycle can be concluded to the work done by the compressor on the system and the heat absorbed in the evaporator is equals to the heat rejected in the condenser. And this equation is still valid and can apply to the actual vapor compression cycle despite the deviation from the ideal cycle. In this analysis, the second law of thermodynamics, especially the entropy changes, will be applied on both ideal and actual cycles. Then we will investigate how entropy generated affects the performance. In ideal compression cycle, the process is isentropic, meaning that it is reversible and adiabatic. As a result, the entropy remains constant, which is S1 equal to S2. This is represented as a vertical line 1 to 2 in the TS diagram. In actual compression, it is non-isentropic due to irreversibility like friction and heat generation. This causes an increase in entropy between stage 1 prime and 2 prime, and the graph is deviated from the ideal cycle. Note that the stage number with prime is referred to actual cycle. Next, moving on to the internally reversible condensation process, the system entropy decreased purely due to the transfer of energy, but there is no generation of entropy without any irreversibility. For actual cycle, due to non-ideal heat transfer and pressure drops, the refrigerant becomes subcold and slight entropy generated. The third process is expansion. In both actual and ideal cycle, this process is not internally reversible. Entropy generation can occur in both cases, but in either case, it is often neglected for simplicity. The last process is the ideal evaporation process. Entropy increases as the refrigerant absorbs heat at constant pressure and the refrigerant evaporates into saturated vapor. This process is internally reversible, so there is no entropy generation. For actual cycle, due to slight pressure drops and heat transfer inefficiency, entropy generation can occur in actual. Finally, we're moving on to analyze the coefficient of performance of both cycles based on entropy generated. We should know that the area enclosed by TS diagram represents the net heat transfer, which implies the work input required for the cycle. In ideal cycle, the enclosed area is smaller than the actual cycle, meaning that less work is needed for heat transfer. As a result, the COP is higher in ideal cycle as compared to the actual one. COP is the ratio of heat absorbed by the evaporator to the work supplied by the compressor. The non-isentropic compression in the actual cycle is the primary reason for the larger enclosed area. This occurs due to entropy generation from irreversibility that leads to the graph to deviate from the ideal graph. In the ideal case, the processes are nearly reversible and the entropy generation is minimized. Then the energy requirement is lower and maximizes the COP. In this section, an online simulation is conducted to investigate the relationship between the pressure of the condenser and also the evaporator and the COP of the system. By fixing the evaporator pressure, the higher the pressure of the condenser, the lower the COP. On the other hand, the higher the evaporator pressure, the higher the COP due to reduce in pressure ratio. Hence, by understanding the relationship between them, the energy efficiency can be improved in the cycle. In the context of vapor compression refrigeration cycle, several technical and non-technical issues can interact, and careful consideration is needed for optimizing system performance. First, the low efficiency refrigeration cycle leads to high energy consumption, driving up the operating costs. Purchase an efficient compressor can improve performance, but it may increase maintenance costs. Hence, by integrating solar power with high efficiency compressor, the system COP can be improved and the energy bill can decrease. Over time, the saving from reduced energy costs offset the initial investment, making the system more economical, viable, and sustainable. The next possible issue is that the traditional refrigerant like R134A has high global warming potentials (GWPS) and can contribute to climate change, while replaced refrigerants to R32 can reduce GWP and improve energy efficiency. However, its mild flammability raised safety concerns during use and storage. To address the flammability concerns, gas detection systems should be installed, particularly in confined space, to ensure safety operation. In conclusion, the first law of thermodynamics states that the energy is conserved and the energy cannot be created or destroyed. And the second law of thermodynamics introduced the concept of entropy, and the energy transformation are not 100% efficient. And both laws are applied to the refrigeration cycle, where the energy conservation and efficiency limits will determine the system performance. And lastly, the problem-solving skills are essential in engineering to resolve the technical and non-technical contradict for optimizing the system performance. So these are the references used to complete the report and also the presentation. Thank you, Doctor.